Honorable Vice Chancellor Professor Rao, our distinguished speaker, Professor Saraswat, other colleagues from BITS-Pilani and other institutions, our dear students, and all other participants to this very important session in this evening. Very warm good evening.
Our own Jagdish Chandra Bose, many people don't know that he was the inventor of the semiconductor rectifier, and uh, he demonstrated the concept of radio 2 years before Marconi, but India was under the rule of British, and he never was recognized internationally till recently. These pictures have been taken out of a museum here in Silicon Valley. In 1930, Julius Lilienfeld patented a three-electrode amplifying device based on the semiconducting properties of copper sulfide. However, he did not demonstrate the device experimentally, and therefore nobody really knows his name. But this is a picture from his patent. It looks very similar to the modern transistor. In 1940, Russell O. and Jackie Scaff at Bell Labs demonstrated p-n junction and the photovoltaic effects in silicon. So that was the first demonstration in silicon that led to the development of junction transistors in solar cells. So this was the beginning of the era in silicon. Britton Bardeen were engineers at Bell Labs, and William Shockley was their supervisor. So Britton Bardeen made this transistor, a huge transistor, point contact transistor in germanium. So the first transistor was made in germanium. Shockley was a theoretician. He explained how it works, and the three got Nobel Prize for their discovery in 1956. And this discovery changed the field of engineering as we see today. Jack Kilby in Texas Instruments was given Nobel Prize in physics in the year 2000 because in 1958, he demonstrated the first hybrid integrated circuit as shown here. So what was the concept here? In a package, there were discrete devices and they were connected by metallic wires. Now, many of you probably don't know that the actual modern integrated circuit was actually developed by Robert Noyce. And his concept is shown on the right side. So this was actual monolithic integrated circuits. So there were devices in silicon connected by wires which were deposited on silicon. Did not share the Nobel Prize with Kilby in 2000. The question is why? I don't think probably people know that fact. He died before the Nobel Prize was given. It's the same reason as Mahatma Gandhi never received the Peace Prize, because before they could consider him for the Nobel Prize, he was he was murdered. Fast forward in 1960, John Atalla and Dawan Kang at Bell Labs demonstrated the first PMOS field effect transistor. And the question is why PMOS first and not NMOS? I'll leave it to your imagination. Although electrons are faster than holes, but for various technological reasons, they could not demonstrate NMOS. So that's my question, why PMOS first? Think about it and ask and discuss amongst yourselves. In 1963, Frank Wanless and C.T. Shah, now the things changed to West Coast. They demonstrated CMOS by having an NMOS and PMOS side by side. And this was the beginning of the modern revolution in electronics. Now, a little bit of history. This is a very complex slide. I'm not going to spend too much time. But these 8 guys, known as Traitors 8, out of these, you may know the names of Robert Noyce and Gordon Moore, as shown here. They used to work for William Shockley. Shockley left Bell Labs, came as a professor to Stanford, and started Shockley Semiconductors with the money he got in the Nobel Prize. And he was a very authoritarian guy. He went around the country and hired these 8 people. Some of them are very famous even today, but these two are the most famous. They got sick and tired of the authoritarian nature of Shockley and founded their own company, which later on became Fairchild. So they stayed at Fairchild for about a decade and made some monumental discoveries. But Fairchild was a East Coast company, still very hierarchical, not believing in innovations that much. So they left and joined a company which later on became Intel Corporation, and that's the history of how developments took place on the West Coast in the United States. Back to famous people. Bob Noyce at IBM in 1968 invented the DRAM, the single transistor DRAM. And little later, in 1974, he came up with the principles of scaling of MOSFET, that you take a larger dimension transistor and scale everything to a smaller dimension transistor through the rules of constant E-field scaling. Till today, we are thankful to Bob Dennard for making these two monumental inventions and development. Then comes Gordon Moore. So from Shockley Semiconductors to Fairchild, he was one of the co-founders and led Intel. And he gave 2 talks. One in Electronics magazine, he didn't give the talk, he published an article in 1965 where he showed a number of components as a function of time, and these were the 5 points. So these did not exist at the time, and this became the Moore's law as we call it today. He again came back in 1975, and in IEDM he gave a talk and added these points, and this thing continues even till today, as I'll show you in a minute. But then he made, this is a sketch from his notebook in 1964, claiming that the cost of scaling will eventually go up. And he had these figures for 1962, 65, and 70. Fortunately, it didn't go up at the time, but today is beginning to go up. In any case, the Moore's law continues. So these are all the way from 1970 to 2018, various data points. On the vertical axis is transistor count, and we are in the billions of transistor count today for a variety of applications. How has this happened? So in early days, we had bipolar transistor as it had been invented at Bell Labs by Britton Bardeen and Shockley. Eventually, each technology reached a limit, and this is what is shown by this curve. So at this point, bipolar reached a power limit, and the CMOS came into being. And then this point, the gate oxide limited came into being. So things like high K dielectric, etc., with materials and memory innovation came through. And then the planar device is reaching a limit today. So we are working on 3-dimensional devices, 3D chip stacking, and advanced power management. So this is the technology today. And as we look to the next generation, we are doing research in nanowire devices, 3-dimensional multi-chip stacking, and photonics. So most of my talk will take you all the way from bipolar to where we are looking in the future today. So this particular figure from Simon Z's book, shows the gross world products and sales volume in various industries. So this is gross world product. So this is global sales in billions of dollars, and this is the time frame here. So as you see, the global world product continues to increase with time. In good old days, automobiles and steel were the driving factors, but today electronics has overtaken even automobiles. I drive a Tesla, and most of the electronics in Tesla is semiconductors. So semiconductors and electronics have become the heart of technology today, and they are very important part of the world economy. So with this history, let me now go to the MOSFET scaling trends. So what is shown here is that from the early days of a MOSFET till the turn of the century, all we did was we actually simply changed the dimension according to the scaling laws of Gordon, the scaling laws developed by various researchers. So simply reducing the gate length. Around the year 2000, we realized that simple scaling of silicon MOSFET cannot go on. So the first thing was straining of the channel to improve the mobility of electrons and holes at 90 nanometer. At 45 nanometer, we introduced high-K and metal gate technology. Actually, my group played a big part in this area. Then at 22 and 10 nanometer, we came up with silicon FinFET, the work done largely at UC Berkeley. And today we are using the nanowire technology at around 7 or 5 nanometer. Now, going in future, we are looking at new materials and device structures integrated on silicon, things like perhaps even 3.5 carbon nanotubes. My hope is very high on two-dimensional TMDs and perhaps maybe SpinFET. So these are the devices in research today. Transition metal dichalcogenides, and I will keep calling them TMDs. To me, this is the most promising technology, but lots of work is going on carbon nanotubes, graphene, tunnel FETs, molecular devices, and spintronics. And as I said, I believe the TMDs will play a major role in continuation of the device technology in this area. So what is the problem? In general, this device scaling methodology does not take into account many other chip performance and reliability issues, for example, interconnects. These factors are now becoming an obstacle in the evolution of integrated electronics. So this work put together by many of the people here in Silicon Valley, including some from Stanford, shows the progress all the way from the inception of MOSFET till recent past. And what it shows is in brown is the number of transistors. And in black here is number of logical cores in a computer. In the middle, these are the two which are very important. The green curve shows the frequency in megahertz. And this sort of reddish brown shows typical power. And it shows that around the turn of the century, both of these saturated. We could not increase the power because of heating problems. And that got saturated to something like somewhere between 100 and 1000 watts. And therefore the frequency was also saturated. The progress in computing has continued through going from single core to multi-core architecture. And the number of transistors continues to increase through this kind of integration. So what is the impact of device scaling on circuit performance? So my colleague, Professor Tom Lee, showed this particular figure. So a few years ago, YouTube users uploaded 72 hours of new data per minute. Skype users connected for 33 million hours per day. Google received over 4 million search queries per minute. One Google search, very sobering thought, Google search, you ask for it, the data goes to the data center and it comes back to you. Through this communication, it consumes about 1 kilojoule of energy, which is roughly one AAA battery. Again, I think, oops. I seem to be somehow frozen. Okay, these applications require high bandwidth, low delay, and low power transition. So in the next few minutes, I'll talk about what are these problems. So if you look at the scaling, not just of transistor, but a chip. So old technology used, so this is sort of schematic transistor, and these are interconnect on silicon. So old technology had small chip area and larger devices. And so the length and therefore the resistance and capacitance, etc., were not main problem. The performance was dictated by the transistor. As we scaled the chip, the transistor became smaller, became faster, but the length of the interconnect across the chip became larger, and resistance and capacitance became much larger. So an old interconnect, which was short in length and fat in cross-section, became skinny, trying to accommodate many more interconnects on the same chip. So a signal going from one end to the other end will get distorted as shown pictorially here. So the bit rate is inversely proportional to the length square and directly proportional to the area of cross section. Power is simply dictated by the frequency and the voltage you are using for transmission. Delay is proportional to length square and inversely proportional to the area. So if you try to improve the bit rate, the delay goes up. So scaled wires with lower area of cross section, longer length, have higher resistance, capacitance, and inductance, and thus reduce bandwidth, higher delay, and higher power dissipation. So this is the main problem with today's electronics technology. So at the turn of the century, my group did some analysis. We came up with a design of a microprocessor. At that time, 50 nanometer was very futuristic. We could not think beyond 50 nanometer. So we designed a 50 nanometer microprocessor. The only thing I want you to see is the power breakdown. So lower half, the green and the yellow, and little bit this part here is because of devices, the logic and the memory mostly. Upper half is all because of interconnect. The signaling interconnects about 27% and clocking about 28%. So more than half the power can be attributed to interconnects in this case. Couple of decades later, my colleague, Professor Miller, did a very detailed analysis. And again, not going in the details, the black part here is energy for logic operations, and the red part here is for communication. And you can see the numbers here that for the devices, or logic operation are in femtojoule or even attojoules. But energy per bit for communication is the smallest one is in tens of picojoules, but energy across communication across the chip is hundreds of femtojoules. So majority of the energy consumption is in communication and not logic. And if we continue on the traditional path, there's no clear path to reduce this energy consumption. So let me go and talk about the interconnect technology. So how can we improve interconnect technology? Perhaps rather than using metallic wires, we could use carbon nanotubes or graphene, or we could use photons for optical interconnects, or we could, rather than going in going in a horizontal dimension, we could communicate vertically. So I will describe, give my point of view on all these three technologies, which are in the area of research today. So why off-chip photonic interconnect? So this is the backside of a rack and data center, and something has gone wrong in these metallic copper wires, and this poor guy is immersed inside this rack trying to figure out what is the problem. All this jumble can be replaced by these optical fibers. So photonic interconnects offer the solution for the future. In fact, quite a bit of communication today is using photonic interconnects. So what is a photonic interconnect? So first, the upper part here. So the red parts are all photonics, and the black parts are using semiconductors or electronics. So maybe you are doing some calculations using transistors and generate an electrical pulse. This pulse can be converted to a photonic pulse using a modulator, which is driven by a laser and converts this electronic pulse to a photonic pulse, which can go through either a waveguide or even in space. At the other end, a photodetector converts it back to electronic pulse, which is amplified and fed to the rest of the electronics. So this could be one single chip, or it could be one chip here and another chip. So the four most important components on which my group has done research collaboratively with other researchers at Stanford are the detector, which is here, the easiest one, a waveguide, a modulator, which is this part here, and the most importantly, the laser, which is on-chip laser is still not solved, but I will give you some idea of where the research is going on on-chip lasers. So 3D integration, first let's talk about that. What is the motivation? So if you consider your cell phone, these are some of the most important parts of your cell phone: the display, the memory, the multiple output, the battery, the MEMS, A to D converter, microprocessor, digital signal processing, and communication link. If you lay them side by side, it will become, this is how the original cell phone was developed. But by stacking them one on top of the other, the footprint can be reduced drastically, in which is what your current cell phone is. It improves the form factor. Furthermore, from my point of view, if this particular 2D system can be represented schematically by this figure here, and this figure on the right side where the chips are stacked by this. So this long interconnect can be replaced by a very short vertical interconnect between these two chips. So this figure shows number of interconnects and wire length. So the red curve here is for the 2D and the blue curve is for 3D. So many of the very long wires like this one can be replaced by very short wires. And therefore, The reduced interconnect length reduces resistance, inductance, and capacitance, and therefore reduction in delay, power, and much higher bandwidths because of reduction in resistance and capacitance. Furthermore, it allows heterogeneous integration of technologies, for example, memory, logic, sensors, and optical I/O. And this is where the modern technology is going today. One example is shown through the PhD thesis of Max Schulacker, which he did in the year 2017. And in fact, his work was so monumental that MIT offered him a faculty position even before he graduated. So this is shown schematically here. This is a wafer from his thesis. And this has 4 layers. First layer is silicon. Second layer is carbon nanotube FET logic. Third layer is a resistive RAM memory. And the fourth layer is carbon nanotube FET and logic. And otherwise long interconnect is replaced by these very short wires. So centimeter long interconnects are being replaced by micron long wires. And these are the views at different magnification, eventually showing carbon nanotubes. And this is a cross section. So this is the technology which is coming up in research today. So why is it so important? Well, people have been predicting that if you show the number of transistors per chip as a function of time frame, it is going to sort of saturate at 11 nanometer node. So people said that the innovation in electronics will saturate and it'll become like steel. Well, in comes the bonding and packaging. So you simply stack chips and use wire bonds to connect, and I call this 2.5D packaging. The next innovation came by 3D bonding. You make 2 chips and bond them together and have actually vertical interconnect. And there, the slope of the technology progress is even better than what it was with just the 2D technology. The true 2D technology is faster than Moore, which is what I just showed in my previous figure, where we stack. And as we stack, we have vertical wires, which are of the nanometer dimension. So I would like to summarize my overall talk as I've been explaining. And first summary shows the technology progression through disruptive innovations. So in the area of devices, what we see from bulk CMOS to silicized to strained silicon, metal gate and high K dielectrics, silicon on insulator. And today we are at silicon FET with some germanium. 3.5 has never really made into the logic, at least. It has its place, but not in logic. So this is where we are today. Unfortunately, in the area of interconnect, we replaced aluminum and SiO2 by copper for conductors and low K dielectrics. And this is where we stand today. From classical physics, we are now using classical physics with some quantum corrections. Going in future, the path for devices is quite clear. We have devices in nanowires, nanotubes, and 2D semiconductors, and eventually maybe spin-fed. So this path is quite clear. However, we will have to resort to quantum mechanical studies of these devices, which we are doing today. The area of interconnect is more problematic. And there we will go and have 3-dimensional systems and optical interconnect. That's my prediction, having spent last 2 decades on these 2 technologies. So future systems will look something like this. 3D heterogeneous integration with conventional silicon devices and other devices and other materials, which I just briefly hinted, and new kind of memories, new kind of MEMS and sensors, metal, carbon nanotube, and graphene interconnects, optical interconnects, and even bio devices. The big problem would be that stacking them one on top of the other, how do you remove the heat? So there will be innovations in thermal management. I didn't touch into that because of limited time, but lots of work is going on by etching these grooves at the backside of a wafer and then passing fluid through these to remove the heat, similar to the radiator in a car. And for energy, perhaps we will be using energy harvesting using sun as a medium. So, well, this is a picture of my recent PhD students, and in some cases their families assembled in my backyard. So I just wanted to show some of my PhD students. And thank you for listening to me with great patience.
Thank you, Professor Saraswat, for delivering such an engaging and inspiring talk today. Your insights have truly resonated with all of us. Thank you once again. And now we open this panel to the question and answer session. Please continue to type your questions in the chat box, and I see one question already. There are many questions. So I'll just read out the question, Professor Saraswat. Maybe you can respond. So this is a question from Vishal Kumar. Respected sir, does TMD-based devices are compatible with the existing CMOS manufacturing processes and facilities? If not, how can this be possibly tackled for large-scale integration?
So look, I get which kind of devices was it? Carbon nanotube or
TMD-based devices.
TMD, okay. So the 2D semiconductors. So the way the technology is progressing, you start with a silicon wafer. Let me go back to even better figure here. Okay, so this can be seen a little better here. So we actually are integrating TMDs on silicon substrate. Today we are in this technology where we were in silicon when I was a PhD student. My thesis was on MOSFETs. And we were literally playing with everything, how to deposit this, how to grow this, how to dope this, and so on. So today's technology is simply making these devices and see if they're feasible. Where we are today, initial work was having the gate electrode on the backside because that's all we could do. But today we are developing technology which looks like this, where we deposit the 2D materials on oxidized silicon and make the entire transistor on top. It is still not there where we can make actually a microprocessor or another large chip, but we are getting pretty close to it. My prediction is that in another 5 years or so, you will see actual use of TMDs in commercial circuits, because the technology is pretty close to what we are used to today with silicon and germanium MOSFETs.
Thank you, Professor. We have one more question from Dr. Rahul Kumar. Why are we struck with silicon-compatible photonic interconnects? Considering the difficulty of light emission in silicon, are there any alternatives?
So we are not really let me see if I can go to anything. I did not really go in great details. Silicon was not meant for photonics. Okay. Silicon was not meant for photonics. So we have worked, and the rest of the community is working on germanium. So if you look at this modulator here, it's germanium deposited on silicon. Silicon is an indirect bandgap semiconductor, but so is germanium. But germanium can be converted into a direct bandgap material by applying strain, and therefore it can be used for light emission. So this work shows a germanium laser integrated on silicon by applying strain in this germanium nanowire when it becomes a direct bandgap and emits light. Similarly, the modulator is made in germanium, and similarly, the detector, which works in 1.3 to 1.5 micron wavelength. The waveguides can be made in silicon, yes. So it's for photonics, silicon is not the answer. It is germanium or maybe another material. Currently, the hope is in germanium.
Thank you, Professor Saraswat. There's one more question from Professor. There's one more question from Professor Srinivasa Prakash Regala. His question is how the 3D printing can contribute to semiconductor devices, because 3D printing resolution didn't yet get below a micron level so far. Basically, he also added a point here that he proposed organic solar PV cell 3D printing to a particular funding agency, but it was rejected because it was not possible. Could you comment on that, please?
So 3D printing is in evolution. The problem is the current technology, and I'm not an expert in the development of printing, but from what I know, it is we are working at nanometer kind of dimensions. So the dimensions of the transistors, not shown here, but the dimension of the transistors is in the nanometer regime, and 3D printing is not there yet. The lithography equipment has become so expensive that there is only maybe one company in Europe which develops that, and the cost is so high that most companies cannot really afford it now. So that's why we are still at 20 nanometer node where we can use conventional means of lithography and not go to 5 nanometer and so on. What was the second part of the question? Oh, the organic. So there are applications where organic materials are used. For example, the latest cell phone technology has some organic screens and so on. Again, I don't know the details, but for conventional electronics or solar cells, let's talk of solar cells. If you are using it on the roof of your home, you would like it to stay for at least 30 years. And today, the life of those solar cells is not 30 years. Not even the organic solar cells, but there are many other solar cells being developed which show the lifespan more like few years. So if your application, like your phone, most people change their phone every 2 or 3 years. So it's okay, but on your rooftop or any kind of other application where you demand much longer life, you cannot use organic materials today. But I have learned how to say never. I showed you that cartoon where I came out of the shell saying silicon will never be replaced. Well, you never know. There are some very clever scientists who may prove me wrong.
Thank you, Professor Saraswat. Yeah, there are so many questions pouring in. I will take a select few because of the lack of time. There's one from Dr. Vidyut Chala. Professor Saraswat, could you please comment on how thermal challenges with 3D IC could be handled?
So I didn't go in the details again. When the given time, thermal challenge is becoming one of the big challenges. And let me see if I can at least have the. So if you stack these devices, even if you don't stack, I showed that the maximum power dissipation has been capped at somewhere a couple of 100 watts. And as a result, the temperature of the chip goes high. So there's lots of innovation in that area. In fact, if you, so I have a cell phone which on the back side of the main chip has actually some liquid which removes the heat from the main part of the chip and dissipates elsewhere. So two things. One is you design the chips so that it is consuming less power, and most of the power is consumed by interconnect. By going from horizontal to vertical interconnect, you will reduce the consumption of power, but still it'll be too high. And in that case, you will have to resort to innovative means of removing power from the chip by embedding. So if you see here, I didn't go in details. These three regions are something like this, means of removing power through some kind of thermal management, which could be what I showed here. Other ways is using materials like carbon nanotubes, which are very highly thermally conductive. So we have lots of carbon nanotubes here, which remove the heat and take it away from your system. So more work is going on in that area at various places in the world. Keep an eye on that.
Thank you. Yeah, I think we'll just go for one or two more questions. I think one question particularly is very important to the current context. The question is from Professor Ram Gopal Rao. What do you think is the way forward for India's ambitious semiconductor mission?
You know, Professor Ram Gopal Rao may remember that when Rajiv Gandhi was the Prime Minister, a group was put together, and I was instrumental in putting together that group from this country and take it to India and suggest that we start semiconductor manufacturing. And Mr. Gandhi was very attentive. He accepted our proposal, and as a result, there were, I think, something like 26 rules were broken to establish some organizations in Bangalore and education systems in IITs and IISc in Bangalore. But then he was assassinated, and the subsequent government did not pay any attention to that. We kept telling the government that this is the goal. Do something. In the meantime, other countries, Taiwan especially, they recruited their leader from USA, put him in charge, and whatever he asked for, they gave him. India did not do that. Now the present government seems to be interested and is making inroads in trying to develop that technology. It's a very difficult path because the amount of money needed from few million of dollars have become multi-billion dollars. But India has to do it. You don't do it, you will remain a second-class power. Let's keep our fingers crossed, and hopefully the present government will go from packaging to larger dimension chips to smaller dimension chips and become one of the leaders in manufacturing electronics in India. And you guys who are much younger will be the leaders in that area. I hope so.
Thank you, Professor, for the encouraging words. One last question, maybe.
Yeah, I think that one question is interesting. What can be the opportunities for startups in the semiconductor area for, let's say, some young graduates from India?
So currently, if you wanted to compete in making a microprocessor at 5 nanometers, you cannot because you don't have infrastructure. But there are many areas which are small volume and larger dimension. Analog circuits, for example, don't rely on 5 nanometer technology. You can still make a 90 nanometer MOSFET and use it for making digital analog kind of chips. Solar cells, we are still importing our solar cells from China. That technology is such that it can be done easily in India. And there are many other examples in medical electronics, for example, which do not need nanometer technology. So it will take another talk to get into those kind of areas where we can make initial investment and from there go to more smaller dimension technologies. That is the path which other countries have taken, and India should take that. I think universities are way ahead of the industry in India. You guys all know what role the universities are playing. There is very interesting research I see being done in universities, but it's not translating to industry as much as I would wish. And that's where I think the present government can play a role in making it more friendly to the chip industry.
In fact, MIT has started a new program called Chip to Startups, and where they are encouraging Indian startups in the semiconductor areas, more in the design IP kind of thing. Yeah. So.
Yeah. I'm keeping my fingers crossed that it will become from small to very large.
Yeah.
India can become one of the leaders in that area. We have everything else except the willingness of the government. They should make investment like Taiwan did and then get out of controlling things, which is what Taiwan did.
In fact, India has done very well in the automotive sector with the Maruti Suzuki and that sort of a model. Probably that's what is needed for even the semiconductor area. So
yes, absolutely correct.
Okay,
Surendra Mohan, I think we need to wind up now, maybe 9:05 already.
Sure, Professor. Yeah, thank you so much, Professor Saraswat, for joining us today and sharing some wonderful insights in this field. And there are so many questions in the chat box, but we are unable to take it today. But I'm sure there will be, we'll have some in-person sessions soon. Maybe we can interact, collaborate, and engage with you in future.
Sure.
I request Professor Rao to share his insights from today's talk.
Thank you, Professor Saraswat, for taking time to be with us early in the morning, your time. And it's also enlightening and so nice to see, an excellent talk. And in fact, I was also saying that the Gordon Moore and Simon Zay, both of them passed away in 2023. I think the two people you mentioned in your talk. So I think may their souls rest in peace. And wonderful talk, and we will be in touch. And I'm sure many people who have listened to the talk would have benefited from this. Thank you so much.
Very welcome.
Thank you, Professor Saraswat. Thank you, Professor Rao. To all participants today, please keep a lookout on our press website about our next monthly colloquia. Thank you all for joining.
Thank you. Bye-bye.